So welcome back for the second lecture of this week. So we had started a formulation of topic models in the last lecture. So but we mainly focused on the basic intuitions. So today we will do the mathematical formulation of latent Dirichlet allocation. So that is the main sort of topic models that I used, also known as LDA. So we were here and we were saying that what is the central problem of LDA. So problem we were saying was that we have observing only the documents, but we know nothing about all the parameters of my generative model. So I do not know what are my topics, what are the topic proportion for the document, and I do not know what is the per document or per word topic assignment. I do not know that. So my real problem is, from my observation, I want to reverse the generative model and come up with all these probabilities. So this figure will help in understanding this goal. So remember, we saw an earlier figure where we had all these topics given to us. We knew what are the topic proportion for this document, and then we were drawing topic for each word in this document. But now, so in reality, I will only have the documents. So I know all these documents, so I know what are the words, but I do not know anything about what are my topics, what are these proportions, and what are these topic assignment for individual word. So I have to compute the distribution conditioned on all the documents that I am seeing in my data. So another simple example to understand the intuition behind the generative model. So here you have some 37,000 text passages from some educational material, and suppose you run LDA, you found roughly 300 topics. So here in this slide, what you are seeing 4 different topics. So you are having a topic like 247, which has word like drugs, drug, medicine, effects, body, etc. Another topic having words like red, blue, green, yellow, white. Another word about mind, thought, remember, memory, thinking, and another topic about doctor, patient, hospital care, and so on. So these are 4 the topics that are there in the corpus by running LDA over these 37,000 text passages. Now, to get intuition about the generative model. So what was the generative model? You have some topics. Now how do you generate documents? You take some of these topics in some proportions and start generating words for that. Now, so suppose you try that. So suppose you take topic 247 and 5. Okay. So suppose I give an equal probability to the first 2 topics. So what kind of document you can generate? Okay, just see these topics. So first topic is about drugs, medicine, person, marijuana. Second, and another topic is red, blue, green, colors. So suppose I blend these 2 topics together. So what kind of document can I generate? Okay, so there can be some different sort of documents you can think of. So one could be that someone who was taking a lot of alcohol, marijuana, and so on, and it affected its color perception. So suppose you want to generate a document like that, you will blend these 2 topics together and write that. Similarly, suppose you want to blend these 2 topics together. Okay, so this topic is about mind, thought, remember, memory, forgotten. Okay, and this is about doctor, medical, nurse, patients, and so on. So if you want to blend these 2 topics together, you will generate a document that says, okay, someone who had suffered some sort of memory loss and it led to visit of the doctor. Okay, so like that, you are having different topics, you can blend some of these topics and generate documents. So this is the generative view. Okay, so we can give equal probability to the first 2 topics that give some sort of documents, and equal probability to the last 2 topics that give me another sort of document. So now this single picture explains both the parts, the generative part and the inference part together. So what you are seeing in the left figure, so this is the generative model. So you are generating some documents, and how are you doing that? So you are having some topics. Suppose you are having 2 topics, topic 1, topic 2. Each topic is nothing but a distribution over words. So you are having some words like bank, loan, bank, money, loan. Okay, so these words are coming multiple times here. So these words are having high probability. On the other hand, second topic has river, stream, bank, river, so on. So these are two topics. Now using these two topics, I am trying to generate my documents. So how can I generate the documents? I'll mix these topics. So suppose I only take topic 1, and I can have a document that contains words like money, bank, loan, and so on. I can just take topic 2 and generate words like river, bank, stream, and so on. But I may also take both these topics in say equal proportion and generate a document like money, bank, river, loan, stream, bank, money. So what you are seeing here in this document 2, the words are labeled with topic 1 as well as 2, because the words could have come from either topic. On the other hand, in document 1, all the words are labeled with topic 1. Doc 3 also all the words are labeled with topic 2, because these are the only topics possible in these documents. So this is my generative model idea. So you have everything here. You have the topics, you have per document topic proportions, and you also have per document per word topic assignment. So you know the topics for each individual word also. Now what is the statistical inference part? So inference part, you only know your 3 documents. So you know my doc 1 contains these words, doc 2 contains these words, doc 3 contains these words. Excuse me. But you do not know what are your topics, and you do not know what are the proportion of various topics that are present in each document. So all these numbers you do not know, and you also do not know for each word what is the topic assignment, and all this you have to infer. So I hope with this figure it is clear what do I mean by generative model and what is my problem, that is to infer all these probabilities of my generative model only from my observation. So now important points about LDA. So first of all, it uses a bag of words assumption. So I hope by now you understand what is a bag of words assumption. That is, I am not looking at the order in which the words occur. So this is like a bag for me. So I am taking all the words and putting them in a set. It's not like a list where some order is important. So LDA does not model the word order as such. So it takes only what are the words present in any order. Second, and I guess you would have also noticed that in the previous example, LDAs are also good at capturing polysemy. So remember what is polysemy? Polysemy is a given word might have multiple senses. So in the case of topic models, what can I translate that? That means the same word might correspond to multiple topics, and this is perfectly allowed because each topic can have its own probability distribution. So that means the same word can come in 2 different topics also. I remember in the previous slide we are having the word like bank that was coming in both the topics, and that is perfectly allowed. So that way topic models can capture whether this word is coming from topic 1 or topic 2 in its different senses. So the way the model is defined, there is no notion of the words being mutually exclusive to the topics. Okay. So for example, money and river can give high probability to the word. So both money and river topics can have high probability for the word bank, and that is perfectly fine. Now to understand the LDA model. So what is the LDA model? So we have to first see what is the graphical notation. Okay. So if you have not gone through some of these graphical notations, so this slide tries to explain how do you interpret graphical notations. So here what you are seeing, I am having some variables. So having a variable y and some variables x1 to xn. So all these nodes that I see in my graphical model, these are random variables. So I have a random variable y, x1 to xn. Now what are these edges? These edges will denote the possible dependence. So here I know that x1 depends on y, x2 depends on y, and xn also. So up to xn all these depend only on y, but they do not depend on each other. So that's why there is no edge from x2 to x1 or x1 to x2. So these depend only on y. Then there is a difference that some are shaded, some are not. So what is that? So observed variables are shaded. So that means these are the variables that I am observing, and this is a hidden variable that is not shaded. And to simplify these notations, what we can use, we can also group some variables together. So some structure that is being repeated, you can put it in a plate notation. So this is you are seeing in the right hand side. So you are having these n different variables, and you can group them together by xn, and you write here capital N. That means xn is repeated capital N times. So this and these are equivalent, and this further simplifies this notation. Okay. So once we have seen this, so how do we interpret graphical notations? Then we can look at the graphical notation for LDA. So what is the so okay, just one more thing, that once we have this notation, we can also compute the probabilities of this the whole graphical structure. So I have variables y, x1 to xn. So the probability would be, I have the probability of y, and each of these depend only on y. So the probability of this whole structure can be probability of y times probability of x1 given y, x2 given y, up to xn given y. So this graphical the structure of my graph also defines what are the conditional dependence between various variables, and that I can use to write my joint probability distribution. Okay, so this is my joint probability distribution over all these variables. So now let us see what is the graphical model for LDA. So you know from the previous slide how to interpret graphical model. So all these nodes are random variables, and observed variables are shaded. Okay, so the only shaded part is WDN. These are my observed words. Everything else is hidden. Now what are everything else? So there are some plates here. So let us see this one, capital K, and what are these topics? So what I am saying here, there are capital K different topics, and each topic is a probability distribution. Okay, so this is the probability distribution over different words for a given topic, for a topic small k. Okay, so beta k is what is the probability of word 1, what is the probability of word 2, etc. for the topic k, and this I am doing for all the capital K topics. Then let us look at this part. So I have capital T different documents in my collection. So for a given document small d, I have theta d variable that denotes per document topic proportions. So for this document small d, what are the proportions in which you are blending different topics together? So this will be different for different documents. So you are having capital D different documents, and there is again a digital parameter here and a topic hyperparameter here. So we will discuss what are these. But right now you can understand by simply this beta k is the distribution over words for a given topic, and theta d is a distribution over topics for a given document. Now let us go inside. So here now we are going to one particular document, and this can have capital N words. And what are these? So you are having per word topic assignment ZDN. Yes, each word will have only one topic, and this is the actual word that you are observing. And these are all hidden. So I do not know what my beta is, I do not know my theta, I do not know my ZDN. So this is only to explain what are my what are different nodes here, what are the different plates here. So you have plates corresponding to topics, documents, as well as the words in a single document, and you have all the variables that we were using earlier, all the notions that we were using earlier. There are variables for each of these. Now let us see what is the actual generative model. How do you generate the words using this structure? So what is the generative model? So firstly, you draw each topic beta I as per the Dirichlet hyperparameter eta. Okay, and you do that for all the k topics. So first of all, in this generative model, you are drawing your topics. Okay, so fine, I have my capital K topics. Now you go to your documents. So for each document, that is small d, draw topic proportions. So you find out what are the topics that are involved in this document as a Dirichlet distribution over alpha. So we will talk about these Dirichlet distributions. What do I mean by these Dirichlet distributions? So you draw a topic proportion, okay, and then for each word in my observation. So for I'm now going to this document. For each word, you draw ZDN as from a multinomial distribution over theta d, and draw a word from this. So draw a topic and then draw a word from this multinomial distribution over beta ZDN. Now, yeah, let's try to understand this a bit more. So let us go one by one. Draw each topic beta I using the Dirichlet distribution over eta. So, so what I am doing here, I have k different topics. So I am trying to draw the proportions, the probability distributions from my vocabulary. So what I am saying, so okay, I have k different topics, topic T1, T2, T3 up to Tk. For each topic I am drawing beta 1, beta 2, beta 3 and beta capital K. And what are these? They are nothing but the probability distribution over my words in my vocabulary. So it can be something like, yeah, this is 0.01, 0.02, 0.05, so on. This can be 0, 0.1. So these distributions are drawn by using a Dirichlet over eta. So Dirichlet is a distribution over distributions. So it helps you decide what kind of distribution will you prefer over another. So that we will again discuss. So this we will discuss later. But the idea is which kind of distribution you will prefer. And this helps you draw some distributions for all the k topics. Okay. Now, so this you have drawn. Now the next line says, for each document, draw topic proportions theta d using Dirichlet over alpha. So now these are your topics, but in your collection you have again capital D documents. So document 1, 2, small d, capital D. So they are capital D documents in your collection. Now what is it? What are you drawing for each document? You are drawing theta d. What is theta d? Theta d is a probability distribution over the topics. So it will be something like, okay, what is the probability of topic 1, what is the probability of topic 2, what is the probability up to topic capital K. So for each document you are drawing these distributions. And what are theta d? Theta d are coming from Dirichlet over alpha. So again this alpha is telling me what kind of topic distributions will I prefer over others. So these are my, so first drawing the topics, then drawing the topic proportion for the documents. Now what else? Now it says, now suppose I am going to this document, then for each word how do you generate words? Draw ZDN as from a multinomial over theta d. So theta d is a probability distribution and it's a multinomial distribution. From there sample one topic. Okay. So this is a distribution over k topics. Suppose ZDN is equal to 5. That is I am taking topic 5. So for each word I will draw one. So it can be whatever that comes according to this multinomial distribution. Suppose this is 5. Now how do I generate the word now? I know the topic. Now I have to generate a word. So I go to, so it says draw WDN from multinomial of beta ZDN. What is ZDN? Now ZDN now is my 5, that is the topic that you draw, and now you take multinomial over beta 5. So that means for beta 5, fifth topic, I will find out what is the, so I will have the distribution, and from there I will sample one word. So I will sample a word from this probability distribution, and that is what I am generating. So this you will do for each of the capital N words in my document, and this is the whole generative model. First you are generating your topics, then for each document topic proportions, then you are going to the individual topic, going to the individual word and generating that word. Okay, fine. So that's what we were saying in this slide. Now, so one interesting point here is, why do we name it as latent Dirichlet allocation? Okay, so we are doing some allocation, but why latent and Dirichlet coming? So, so latent in this LDA has the same sense as in latent semantic indexing. So that is, all these topics are some sort of latent variables. Okay, so they are some sort of hidden topics, some latent topics. I do not know what are these topics as such. I cannot give them a maybe good labels also, but there are some distributions, some hidden distributions over my words, and these are called latent. Then what is Dirichlet here? So you saw the Dirichlet distribution at two places. So that is the distribution that is used to draw the per document topic distributions is a Dirichlet distribution. Okay, so that is how am I sampling topics for a given document that is coming from a Dirichlet distribution, and this result is used to allocate the words of the documents to different topics, and that's where the word allocation is also coming. Okay, so you are having latent, Dirichlet, and allocation. So now we will look at this Dirichlet part in bit more detail. So what are the Dirichlet distributions? So if you think about it, so if you intuitively try to understand that, this is a distribution over probability distributions. Okay, what do I mean by that? So the Dirichlet distribution is an exponential family distribution over the simplex, that is the positive vectors that sum to 1. Okay, so when I talk about simplex, so you can talk about, say, one simplex. One simplex would be two elements, say x1, x2, such that x1 plus x2 is equal to 1. Positive vectors that add up to 1. This is one simplex. So you can see that there are infinite solutions here. Okay, and you can treat it as a line. It's a line, and this might correspond to, say, 0, 1. This might be 1, 0. So that is topic 1 has 0, topic 2 is, or yeah, x1 is 0, x2 is 1. Here x1 is 1, x2 is 0. And any point you can accordingly give some definition. What are the values of x1, x2? Okay, so you can see that this will be a line, simple line, x1 plus x2 is equal to 1. This is my one simplex. Then you can have two simplex. So then you are having three things, x1 plus x2 plus x3, they are to 1. Okay, and this would be some sort of triangle. Okay, so this point might correspond to, say, x1 is 1, x2 is 0, x3 is 0. This might be x1 is 0, x2 is 1, x3 is 0. This might be 0, 0, 1. And then each point will have some proportions such that all three add up to 1. This is my two simplex. Like that you can define of any n simplex. So if you are having k topics, you can think of it as k minus 1 simplex. Okay. So now what is my Dirichlet distribution? So now we are saying it's an exponential family distribution over the simplex, that is the positive vectors that add up to 1. So again, let us try to understand that intuitively first. So what I am saying here, suppose I am having a two simplex, then lot of different values, my three x1, x2, x3, they can take a lot of different values. So I can take values like 1, 0, 0. I can take values like 0.33, 0.33, 0.34, and things like that. They can take a different values like 0.5, 0.25, 0.25, etc. So what my Dirichlet distribution does, it gives me a probability of this probability distribution. So what is the probability of getting a distribution like this? What is the probability of getting a distribution like this? Okay, so that is what kind of distributions I will prefer. So I can use that to say that I'll prefer distributions where one of the topics has a high probability and others have very low probability. Or I will like to have a distribution where all the topics have equal probability. So these kind of constraints you can put by using your alpha. Okay. So that's where the formulation is. So what is the probability of theta? That is a distribution over these topics given my alpha, that is some gamma function. So even if we forget about this term, so this is multiplication over theta I to the power alpha I minus 1. Okay. So let's look at this term only. So what is being said here? So probability theta given alpha is multiplication over theta I to the power alpha I minus 1. Okay. So let's try to understand that. Suppose my alpha I is say 0.1 versus alpha I is equal to say 2. What would happen in the two cases? And let us say I look at two different thetas. So my theta 1 is 0.98, 0.01, 0.01. Okay, one topic has a high probability, others have roughly 0. And theta 2 is say 0.33, 0.33, 0.34. And now you can see what kind of alpha will prefer one theta over another one. So let us take the case with 0.1. Alpha is 0.1. So what will be the probability of this getting this distribution? It will be 0.98 to the power minus 0.9, 0.01 to the power minus 0.9, 0.01 to the power minus 0.9. Okay, and this probability would be same 0.3 to the power minus 0.9, 0.33 to the power minus 0.9 and so on. On the other hand, if I take alpha is equal to 2, then this would be 0.98 times, so alpha minus 1 will become 1, so the power is 1, 0.01 times 0.01, and this would become 0.33 times 0.33 times 0.33. Now what is your observation here? So one thing we see it that if you take alpha is equal to 2, if you take alpha is equal to 2, then the topics where, so the distribution where one topic is having very small probability will get a overall very small probability, right? You multiply 0.98 by 0.01 times 0.01, this will become very small. On the other hand, this will be okay. This is like 1 by 3 times 1 by 3 times 1 by 3. So as you increase alpha, it will prefer to have topics or the distributions where each topic probability is roughly equal. Okay, so it will prefer this one. But if you are having a smaller alpha, then what you are seeing? So now 0.01 to the power 0.9, this will be now can be written as 100 to the power 0.9. Okay, so these will become very large, and this will be roughly, this will not be large. Okay, so what will happen as your alpha becomes small, they will prefer the probability distribution where one topic is having a high probability and others are having low probability. So by tuning your alpha, you can prefer one topic probability, one sort of distribution over other distribution. Okay. So this is my Dirichlet distribution. So now again to give you some visualization, so here are two different sort of simplex. So alphas as such you can interpret as some prior observation count on the number of times a topic j is sampled, individual alpha j's. So that is how many times this topic will be sampled. But so and you can also think of as some forces, and higher alpha will move the topics away from the corner of the simplex. So let me come back to this point again. So you are seeing two different simplex, one where the topics are moved away from the corners, okay, these are being moved away, and here you are going towards the corners, and this is for because of higher values of alpha, and we will come back to this again. So now when alpha is less than 1, there is a bias to big topic distributions favoring just a few topics, and this is what we saw just now on paper, that when alpha is less than 1, it tends to prefer the distributions where only a few topics has a high probability and others have lower probability. Now, while in general you can take different alphas for your different topics, what is convenient is that you take all alphas to be the same. So you have a single hyperparameter alpha. So all alphas are same. Now what matters now is what is the value of this alpha. Okay, so relatively they are the same. All alpha 1 to alpha alpha capital D, all for all the documents they are the same. Sorry, alpha 1 to alpha capital K, they are same. But what is their relative number? Is it like, what is their number? Is it like 0.1, 2, 5? That will matter. So now if alpha is small, what will happen? You will tend to prefer topics with you will tend to prefer distributions where one topic will have a higher probability. So remember, how did we define simplex? So in this case, what this boundary means? So this colors denote what is the probability distributions. Okay, so black means a high probability distribution, and so on. And as it diminishes, so the color becomes so faded, then you are seeing that the probability is decreasing. So in the left hand side figure, the probability is mostly centered for in the center of the simplex, while in the right hand side it is moving towards the corners. Okay, so that you can interpret as if in this simplex, whenever all three topics have the same weight, it is given a higher probability. Here, even if one topic is having a more proportion than others, it is getting a high probability. So this is now moving away from the center of this simplex, so going towards the corner. So if you go to the corner, that means one topic has the high probability, other two have the small probabilities. Okay, so this is favoring also to have topics where, also to have distributions where one topic has high probability than others, while this will favor the distributions where all three topics have roughly equal probability. Okay, so now you can easily tell which one is corresponding to higher alpha or lower alpha. So the one that corresponds to lower alpha will be like that. It will favor distributions where one topic is having a high probability than others. Now this is some from simulation. What happens if you take different values of alpha? So if you take alpha is equal to 1, what kind of distributions are preferred? So there are 15 documents here that are being shown, and there are 10 different topics. So we see the distributions are okay. So you are having some distribution for topic T2, T3, and so on. For these 15 documents, there are different distributions. But suppose you try to now increase the value of alpha as you go to 10. So as you increase the value of alpha, it will start favoring those distributions where all the topics have roughly same probability. You see now this is getting flattened. So you are now seeing all the topics. And if you try to increase alpha to 100, you will see all the topics have same probability. And this is not something that you will anyway desire. So it's not good that each document has all the topics in same probability. Then the topic model does not make any sense. So alpha is equal to 1 was looking okay. So this kind of distribution we would like. But now suppose I want to decrease the value of alpha. So suppose I go from 1 to 0.1. So now what you are seeing, it will start favoring the distributions where one topic has a high probability, or 1 or maybe 2. Okay, but suppose I decrease it further to 0.01. So most of the topics have probability 0, only one topic comes as a probability 1, or here 2 topics are coming. If you further reduce this value to 0.01, you will get only one topic in each document. So that will give you some idea of how, if you modify or change this parameter alpha, how does this affect the overall topic distribution in my corpus. Okay, certain kind of distributions will get preference over others. Now for LDA, there are a lot of implementations that are available. So and these are like very popular. You can also use implementations that are available in Gensim. So now, we have discussed only the generative part, but now in full details, that what is the generative model of LDA. But remember, what is my problem? How do we infer all these probabilities? So that is, I am given a collection of documents and I want to infer per document topic assignment ZTN, per document topic distributions theta d, and per corpus topic distributions beta k. I want to infer all this. Now, once I am able to infer all this, I can use this to find out, let's say, for information retrieval, document similarity, and many other tasks. But the question is, once I am given these observations of the words, how do I infer all these probability values? So there are different ways of doing that. So we will discuss about one such method in the next lecture. Thank you.